Alright, this is winter 25, paper 22 that we're now starting with. Let's get right into it. Question number 1. Scientists are investigating the variation in air pressure at different locations on a mountain. Scientists take measurements of several physical quantities, and you basically have to identify with a tick, stating the SI base unit for each quantity and identifying with a tick whether it's a scalar or a vector. So SI base unit of this is the Kelvin, which is basically K. Again, there's no degrees with the Kelvin, and it is a scalar, right? And air pressure, so it's asking for SI base units. All right, so base units of pressure, so you'll need to work this out. So pressure is force over area, and force is kg ms minus 2, area is m square, so this becomes kg m minus 1 s minus 2, and this is also a scalar. At one location, the density of the air is this much spherical, where the balloon is filled with the gas and released from rest. The balloon has a radius of this much. Calculate the upthrust acting. So U equals rho g delta V, rho being 1.1, g being 9.81, volume by 4 by 3 pi into r cube. So this turns out to be 33 newtons. Explain why an upthrust acts on the balloon. Again, we just did this question in the previous paper, which was winter 25, paper 21. So we'll say that there's a difference in pressure between top and bottom, since pressure is proportional to depth. So I would say the pressure upwards on bottom surface, or you can just say the force so the force upwards on bottom is greater than force downwards on top, causing a resultant force upwards. Alright, the balloon has weight 19 Newton. Calculate the magnitude of the initial acceleration of the balloon. So upthrust is 33, this is 19, so 33 minus 19, so I'm using resultant force equals ma, and the mass I'll find using 19 over 9.81, because that's the weight, so W by G gives us m into a, right? So from here on out, you'll just rearrange and you'll find a to be 7.2 meter per second square. A quantity C relating to the motion of the balloon is calculated from 3 measured quantities using this formula. Okay, so C is calculated, alright, and it's also the subject. So percentage uncertainty is given in 1.2, calculated value of C is 1.8, determine the absolute uncertainty in C. So first of all, I can see, because everything's being multiplied, divided here, percentage uncertainty in C is percentage uncertainty in K plus percentage uncertainty in F plus twice your percentage uncertainty in V. So in K this is 5, in F this is 3, in V this would be 2 times 4, which is 8. So 5 and 3 is 8 and 8 is 16%. So delta C, this is your absolute uncertainty, 16% of 1.8. This turns out to be what? Let's see. So this is 0.288. So your actual value is 1.8 plus minus 0.288. So this becomes 0.3, right? So 1.8 plus minus 0.3. Okay, it's just asking for the absolute uncertainty. So yeah, just 0.3. Remember to give your absolute uncertainty always to 1SF. A spacecraft in deep space uses jets of hot gas from its thrusters to change its velocity, and 2.1 shows a side view of these spacecraft and some of its thrusters. So there's thruster A, thruster B, thruster C as marked. Distances are marked from the center of gravity of the spacecraft, which is shown to be here. Thruster C is at a distance of 0.4 meters upwards from the COG. Thrusters A and B can produce forces on the spacecraft in the upwards direction only. Thruster C can produce a force in the leftwards direction only. All thrusters shown produce forces entirely in the same plane as the center of gravity. Thruster A is activated, producing a force of 60 Newton upwards on the spacecraft. Alright. C is also activated, producing a force of 220 leftwards on the spacecraft. Calculate the resultant moment due to these forces about the COG. So at A, this is 60 upwards, and this is 220 to the left, right? So this is producing a clockwise moment about the COG. This produces an anti-clockwise moment. Obviously, both will be subtracted. So that's 60 into 1.6 minus 220 into 0.4. Right? 60 into 1.6 is anti-clockwise, minus 220 into 0.4, so that's 8, right? And obviously this is 8 anti-clockwise, because the anti-clockwise moment was greater. That's why my answer here is positive. So state and explain whether the forces from A and C are a couple. So obviously not, because they're not equal magnitude, they're not parallel, and they're not acting in opposite directions, so not a couple. So I can say not parallel, so not a couple. Alright, so you just have to give any one reason. Thrusters A and C are now switched off, and the spacecraft is stationary. Thruster B is activated at time t, producing a constant force on the spacecraft until the fuel runs out at a time t2. As the fuel is used, the mass of the spacecraft decreases. Sketch the variation of the speed of the spacecraft with time from t1 to t2. Okay, so we have to sketch the speed time graph, and again we need to remember that the gradient is acceleration, right? And the acceleration is basically also linked to F, so it's F equals ma. Alright, so acceleration equals F over m. So in this case it says that the force is constant, but the mass decreases. So what's happening to the acceleration? The acceleration is increasing here, because even though the force is constant, the mass is decreasing. So the gradient of this graph is increasing, which means it's supposed to be an upward sloping line like this, an upward sloping curve like this. Alright. Next, spacecraft now splits apart into a carrier and a payload as shown. During the split, an average force of 5500 Newton acts on the payload for a time of 0.36 seconds. Velocity of the payload increases by 8.5 meters per second in the upwards direction. Combined mass is this much. State the principle of conservation of momentum. So for closed system, total momentum is constant. Show that the mass is 230 kg. Alright, so it says that an average force of this much acts on the payload for this time, and the velocity increases by 8.5 meters per second in the upward direction. So F equals delta P over delta T, which is m delta V over delta T. So m is F delta T over delta V. F is 5500, delta T is 0.36, delta V, the increase in velocity, that's 8.5. And I think it was also initially told that it was at rest initially, right? And even if it wasn't, So basically, let's say if the initial velocity like this is 0, so afterwards it increases by 8.5, right? So the final velocity would be 8.5 plus u, like that. So yeah, that's how you do this, and you should be getting that exact same thing. Yeah, so this is 232.9, which is what you're looking for. Calculate the magnitude of the change in velocity of the carrier. Alright, so this was the change in velocity of the payload. Now it's asking for the change in velocity of the carrier. Now how can we do this? So if an average force of 5500 acts on the payload, I can also say because of Newton's third law, an equal force also acts on this guy. Right? So if I do that, I'll say, because this is a Newton's third law pair, right? So F acting on this guy is also 5500, and I can do the same thing, M of the carrier. So combined mass of carrier and payload is this much, right? So the mass of just the payload is this much. So the mass of the carrier is this minus this, right? So 2.5 into 10 to the 3 minus 230. This is M, right? So this is what I'm using. This is delta V, and delta T, obviously because of Newton's third law, that's also going to be the same, which is 0.36. So 5500 into 0.36 over 2.5 into 10 to the 3 minus 230. This turns out to be 0.872. So 0.87 meters per second. Alright, not really, again, a very difficult question. A spring is fixed at one end and attached to the frame of a pulley at the other end. A cable is passed around the wheel of the pulley. The spring is stretched to a fixed length using the cable and the pulley. 3.1 shows the view from above of the spring, cable and pulley. Spring obeys Hooke's law and has a spring constant of this much. A force F acts on the spring. Tension in the cable is T. The pulley is in equilibrium. Draw labeled arrows to show the direction of forces acting on the pulley. So tension in the cable, where is the cable? Okay, that's the cable. So tension in the cable is like that. So basically that's like this and this, right? So that's how the forces act on the pulley, because tension is always marked away from the object being considered, and the force on the spring, that's basically going to be like this. Again, because of the same reason, because this is also really tension, it's marked away from the object we are considering, which is your pulley. Force F is 110, determine T. So this is a simple equilibrium of forces. So F equals 2T. So T equals F by 2, which is 55. 110 divided by 2. Calculate the extension of the spring. So you know of the spring, you know the Hooke's, you know the spring constant. So F equals Kx. So F was 55. K is 250, and then you need to find X, right? Oh, just a minute. Force F is not 55, that's T. This is 110. So 110 equals 250X. So X equals this, right? Which is 0.44 meters. A second identical spring with the same spring constant is now also connected. The tension in the cable is kept the same. The pulley is again in equilibrium. Determine the extension of these springs. So obviously now the force exerted on the spring, which was 110 previously, that's also going to halve. So there's going to be 55 here, 55 here. That's how springs in parallel act. So I'll use F equals Kx again. Obviously this is going to be 55, this is going to be 250 still. This is X. So X is 55 over 250. That would be half of the previous part. So 0.22 meters. elastic potential energy stored in the spring is 3.1 is E1. Total elastic potential energy stored in the two springs is E2. Calculate the ratio E1 to E2. So in one spring, okay, so it says in total, no, wait a minute. Elastic potential energy stored in the spring in 3.1. Yeah, that makes sense because there was only one spring here, right? So the force was 110, so I can use half Fx. So F was 110 and X is 0.44. That's E1, half into 110 into 0.44. And the total elastic potential energy stored in the two springs is E2. So basically in this case as well, you can say that the energy stored in one of the springs, and then I can double it, right? Which is half into 55 was the force on each spring, and the extension is 0.22, and then I can just double this, right? So yeah, this is what it is, and then you just solve this expression. So this turns out to be, let's see this, so this and this, so yeah, this is just 2. Alright, let's go on. A laser emits visible light of single frequency in a vacuum. The light is incident normally on a double slit and then forms a pattern of bright and dark fringes on a screen as shown. Separation of the slits is this much, distance is this much, and distance between centers of dark fringes is 3.3. Explain how the pattern of bright and dark fringes is formed. Now technically here you should be writing 4 points, but the examiner is giving the third mark for if you write one of those 2 points for the third mark. But the first 2 marks, those you get like this. So light diffracts at the slits, light from each of the slits superpose, and where the phase difference is 0, or when you can say where the waves meet in phase, the bright fringes are formed, and where they meet out of phase, where the phase difference is 180 degrees, then you have your dark fringes forming. Alright, Ci stands for constructive, Di stands for destructive. So Ci is basically, it means your bright fringe, and that's how I should have also written this. Di is your dark fringe. Alright, calculate the frequency of light emitted by the laser. So we can just use the double slit formula. So lambda equals Ax over D. So A is 1.0 into 10 to the negative 3. X was written as 3.3 mm, right? And D is 4.8. So from here on out you'll get 690, I think. That's lambda. And once you have that, then we can use that, because this is a laser, so this is visible light. We know that it travels at the speed of light. So 3 into 10 to the 8 divided by the wavelength would give you the frequency. So that turns out to be 4.4 into 10 to the 14 hertz. Alright, then it says the double slit is removed and a second laser is placed beside the first laser. It says that the second laser produces visible light of a different frequency from that of the first laser. Beams of light from the two lasers overlap. Explain why a steady pattern of bright and dark fringes is not formed. So that's the reason for using a single light source in the double slit, is that it takes care of coherence. So you'll say that they are not the same frequency and do not have a constant phase difference, right? So they're not coherent. All right, let's go on. With this question we'll do it together. So question number 5.1 shows a circuit containing a battery, two fixed resistors X and Y, and an LDR Z. The battery has EMF 5 volt and internal resistance 4.7 ohms. Current in X is I1, current in Y is I2, as shown here. resistance of X is 100, resistance of Z, which is an LDR, varies with light intensity as shown. So it says, again, state Kirchhoff's first law, pretty straightforward. At a junction, sum of currents entering equals sum of currents leaving. Let's try out the other parts of this by ourselves. Intensity of light incident on Z is 130 watts per meter square. Current in the battery is 38 milliamperes. Show that the terminal potential difference is 4.8 volts. So intensity of light, when this is 130, so that's on the x-axis, so that's here. So the resistance seems to be 120 ohms. So this is the resistance of Z, right? So this is 120. And what else did it say? It says that current in the battery is 38 milliamperes, which is 0.038, right? So this is 0.038. Right? So 1, 2, 3, yeah. Still have to do that sometimes. Show that the terminal potential difference is 4.8 volts. So terminal potential difference is basically what appears here, right? Or you can also just do this, Vt equals E minus IR. So Vt is 5 minus 4.7 times 0.038 E minus IR. That's this. So let's just copy this. And this value, that does turn out to be 4.8 volts to 2SF. Calculate the current I2 in Y. So now that I know the terminal potential difference, which is 4.8, now for Y, do I know the resistance of Y? No, I don't, but I know the current here, and I can find out the current here, and then I can subtract, right? So the current I1, that's going to be the terminal potential difference 4.8 over the total resistance, which is 100 plus 120, which is 220, right? So what does this turn out to be? Let's work this out. So 4.8 divided by 220. This is 0.0218. So the current I2 would be 0.038 minus 0.0218. This turns out to be 0.016 amperes. Right, so that's the answer to this. Next part. Calculate the power dissipated in Y. So I know the current in Y, I also know the voltage because it's the terminal potential difference. So that's simply P equals VI. So terminal potential difference was 4.8. The current you just found is 0.016. So just multiplying the two of these, this turns out to be 0.077 watts. Intensity of light incident on Z decreases. State and explain the effect on the terminal potential difference of the battery. So terminal potential difference, again Vt equals E minus IR. So if the intensity of light on Z decreases, being an LDR, the resistance of Z is going to increase. So the total resistance is also going to increase, right? So if the total resistance increases, then the current supplied by the battery decreases, right? And if the current by the battery decreases, so there is less volts lost against the internal resistance, right? So if less volts are lost against the internal resistance, so Vt, terminal potential difference, is going to increase, right? So that's that. State what is meant by a fundamental particle. So a particle that cannot be divided or split into smaller particles. Particle Q is a meson with a charge of 0. Determine a possible quark composition. So a meson is a quark and an antiquark, right? So how can I have a charge of 0? So UCT upcharge top R positive 2 by 3e, right? And DSB downstrange bottom is negative 1 by 3e. So I could pick up, let's say, one of these and one of these antiquarks to make a total charge of 0. So like down and anti-strange, right? Something like this. And yeah, or I could have also done, for example, something like up and anti-charm or up and anti-top, anything of this sort. So that's all fine. Particle Q has a mass of this much, kinetic energy of this much. Calculate the speed. So EK is half mv square. So 2.1 into 10 to the negative 16 equals half. The mass is 0.67 and U in your data sheet, that's 1.66 into 10 to the negative 27 into V square. So from here on out, you just solve for V. So that's 6.1 into 10 to the 5 meters per second. Radium is a radioactive nuclide. State the number of electrons in a neutral atom of this. That would equal the number of protons, which is 88. A nucleus of radium undergoes a series of decays to form nucleus X. During the process, 5 alpha and 4 beta negative particles are emitted. Determine the number of protons and the number of neutrons in nucleus X. So if I talk about the alpha, so this is 228 and 88, this is radium. Let's first talk about the alpha. So because of the 5 alpha decays that happen, each alpha decay will reduce the let me call this Y, will reduce the nucleon number by 5 times 4, right, which is going to be 228 minus 20, which is 208, and the proton number by, because each alpha is 2 and there are 5, so 88 minus 5 times 2 is 10, so 78, and then it decays further into X, and these are your 4 beta negative. So for X, no change to the nucleon number, and 4 beta negative means that this is going to increase by 4, this is going to become 82. So number of protons 82, number of neutrons 208 minus 82, which is 126. So that's this winter 25 paper 22 paper. Hope this helped. Again, not a really very difficult paper, I would say pretty standard difficulty. So that's it for this video, and I'll see you in the next one. Bye.